Okay, so we have this definition of the derivative of a function from an open set in Rm to Rn at a certain point. And this definition is the direct generalization of a definition in the single variable case, but understood appropriately. So the derivative is now no longer a number, but it is a linear map, right? Such that the limit that I have written over here is 0. So let us say I of, so let's call this alpha of A, or let's still call it the same, R of H, where RH, R is a function which takes a vector H in Rm, right? Because remember, I'm one second. Yes, so this is in Rm because I'm evaluating the function f at A plus H. And H is a small vector. I can take H to be any small vector within a certain of a certain bounded size. And the reason for that is because I have taken U to be an open set. So given any point A in that open set, I will have a small ball of a certain radius around A, which is contained in U. All right. So where R of H is what? It is f of A plus H minus f of A minus TH. Again, remember TH is the linear operator T applied to H. Very good. We have seen so far that when the derivative, when such a map T exists, there is only one such map, right? So the derivative, if it exists, is really the derivative. It is unique. Now we have a new concept, which is a natural generalization of the one variable concept when you formulated it suitably. We have a new toy, and anytime we have a new situation, we really should play with it to see how it behaves. We need to put this, it's like you encountered a new animal, you put it in various situations and see how it behaves to understand its overall behavior. So we have to play with this concept, see many examples to see what phenomena occur. So some intuition that is coming from just one dimension will be valid, but it will display many different kinds of behavior, right? That we will slowly uncover using many examples. But first, we have to do some basic things. So what are those? And one is to relate this to partial derivatives that we are familiar with. So let's go in that direction. And let's see the special case first. So special case.
Hello, sir.
Yes.
So I had one question.
Yeah.
In the previous class, while defining this definition of the derivative, you told that the norm of h tending to 0 is same as saying that h tends to 0.
Right.
I mean, I know the fact that if norm of h is 0, if and only if h is equal to 0, but can this statement be formally proven? I mean, that
okay,
h tends to 0 is equivalent to saying norm of h tends to 0.
Okay, so let's see this. So let's write this in. What does say limit h approaches 0 of something, some function of some function of h equal to something, let's say some L. Let's say f of h, not f, some other function. Let's say g of h. What does it mean? Where h is in, remember h is in
Rm.
Right. and f is a function from, and let us say f is, and this contains some set u, and f is a function to some Rn. What does it mean?
So G, right?
Sorry, G, yes. Thank you. What does this mean? We have to have a definition of this, right?
Yes, sir. So given any epsilon, I have a delta such that whenever norm of x minus h
Right,
is
so
less
they
than
exist,
delta.
right? Such that norm of h. So you see, you are taking norm of h over here.
Oh, okay, yes, sir.
So you see, just by definition, it really is identical. There is nothing to prove over here.
Yeah, yes, sir.
Right? Such that norm of h less than delta implies whatever, correct? So taking limit as h approaches 0 and taking limit as norm of h approaches 0, they are both exactly the same thing.
Yes.
Okay. So this is just a simple comment. All right. So special case. And that is when my function is, let us say, u is just a subset of r to Rn. So in other words, this is a vector valued function of a single real parameter. But in that case, what is this? F is just F1 to Fn, where each Fi is just a function, just a real valued function, right? So in this case, what is F prime of A? Let's write down this definition. So what is,
Sir, this is with respect to the standard basis, right, of Rn.
Okay. So
Okay.
what does it mean? Right. So what does it mean with respect to standard basis? What do you mean?
I mean the components F1, F2, Fn.
Right, exactly. So, but remember, Rn as a set is really just a tuple of numbers. So there is no ambiguity over here.
Okay, sorry.
Right. So let's just look at the definition. I mean, there is nothing to this. So what we have is that limit as h approaches 0 of f of a plus. Okay. So h is really just coming from real numbers, right? So let's write down what a is, just sort of to be. And okay, so let's sort of say that this is the transpose. Because you see, I want to write elements of Rn as column vectors. So this is really F1 of A plus H up to Fn of A plus H. That's what F is. Minus F1 of A up to Fn of A. Correct? Minus. And then I have to take some linear operator applied to the real number h. But some linear operator applied to this real number h is simply going to be multiplication by a scalar in each fixed slot, right? So this is going to be, okay. I'm making maybe more of a big deal of this than is required. But you see what needs to be here? This is time minus t of h, and this limit needs to be 0. But the top is a column vector. So what that means is that this t of h is, so t of h, where t of h is again a column vector, right? So let's call this to be something. In fact, let's not make a notation. So this will work. Let's make a sentence of this. So this will work. Precisely when? Precisely in what case? Remember, T of H is a column vector. So there are going to be n slots written over there. What has to be written in the top slot for this limit to be 0?
Derivative of f1 into h.
Exactly. And likewise in every slot, precisely when T of H is equal to f1 prime of A all the way up to fn prime of A. So what is happening is that in this case, where I have a vector valued function, taking its derivative as a linear map really just corresponds to just taking the derivative in each slot. Okay, but let's sort of persist this a little bit. So what is the matrix of T here? So remember, T is a map from where to where? It's a map from R to Rn, because your original function itself is from one dimension to n dimension. So this matrix will be of what type, what size? Must be of size what by what? So this is a map from R1 to Rn. So the matrix must be
N cross.
n cross 1. In other words, okay, so this needs to be, and so what is the matrix? Oh, sorry, by the way, I made a mistake over here, and nobody sort of pointed this out. I wrote T of H here. So what should T of H be?
Yes, sir. We should multiply by h.
I should multiply by H everywhere. And so the matrix of T must be of size n by 1. And it is clearly, it is. So let me just write this. F1 prime of A up to Fn prime of A transpose. Okay, so maybe I discussed this at too much length. The point though is that in this particular situation, what happens is that to calculate the derivative is really just the same as calculating the derivative of each component function with respect to your source variable. Now, let's see this in general. Okay, so more generally. So the question. What is the matrix of F prime of A with respect to standard basis of Rm and Rn? And so I said this last time, so recall for A, or rather the answer of this question is something that you should have seen at great length in your linear algebra course last semester. So recall, or let's just say the answer. So what do I do? Jth column. So let's do one thing. Rather than writing F prime of A, let's give name to it, T. Jth column of matrix of T is simply T applied to Ej. And remember this way, this is a vector which is in where? This is a vector in Rn. So I'm back to the more general situation, right? Which is I have an open set in Rm and I am calculating its derivative. I am calculating the derivative of a function from that to Rm. Okay, so let's do this. So I want to calculate T applied to Ej, right? Okay, so let's do the following. Let's go back to the definition. Yeah. So this definition here at the end of the red arrow, this tells me how the derivative applied to any small vector h is, or how that behaves when I put that into this limit that I have written over here. But you see, I have control over the operator t only when h is small, whereas I want to apply this to the vector ej. And the norm of ej will be some fixed number. I mean, I cannot take the limit of that as something goes to something. It's just a fixed thing. And in our ordinary norms, it is just 1. So what is the way around this? And it's very simple. It's something that we have seen before.
So,
I think of, yeah, what do I do?
so we could take a lambda, we could take lambda into EJ and then let
Right.
lambda go to 0.
So basically, I think of EJ not as a fixed vector, but I take all scalar multiples of that, and that scalar multiple I can vary, and I let that go to 0. So in other words, I vary that along that direction, and I fall into 0 along that direction. So that's a simple idea. So so look at this limit, and I will so what will I do? I will simply take h to be some lambda times EJ. So let's write that down. So limit as h approaches 0 of f of a plus lambda times ej minus f of a divided by, okay. So now I wanted to take h. There is no h over here. So it's the lambda times ej that should approach 0. Right? And so I will change simply my name. And instead of taking limit as h approaches 0, I'm taking the limit as lambda approaches 0. And so in the bottom, what do I write?
Modulus of lambda.
Right, except I can write mod of lambda times ej. Right, really just to so okay, so first of all, this is minus t of lambda ej. So what do I know about this? So I know that this limit is 1. Sorry, I know that this limit is 0 by definition of t equals f prime of a. Yes. Okay. So let's just look at this and see what it gives me. So what can I do over here? It's a pretty simple thing now. All that I have done over here is that in the definition of the derivative, I have plugged in h to be lambda times ej. And whenever h goes to 0, this limit is supposed to be 0, right? So in particular, if lambda goes to 0, then it's a particular way of sending this vector h to 0, namely just along the single line. So what I have written over here is a consequence of t being the derivative of the function f at a. All right, so let's do some calculation with this. Can I do anything with this?
So we can take lambda outside.
Lambda outside where? In 3 places lambda is inside. Where can I take it outside?
Denominator.
Yes, but also in another place I can take it outside. Remember, t is
of lambda is
right. So t is a linear map. So when I apply to lambda times ej, I get lambda times t of ej. And I like that because I do want to calculate t of ej, right? Okay. So let's write this t of
And denominator mod lambda will come out.
Yes, by linearity of t. And lambda ej is equal to mod lambda times ej. And let us say I will just take this to be lambda. Notice I can take any norm I like. Yes. So I just take, let's say, the usual Euclidean norm, or the max norm, or the p equal to 1 norm. Doesn't really matter. In all of those, the norm of ej is 1. Okay, so what does this give me? So therefore, this gives me that limit as lambda approaches 0 of f of a plus lambda times ej minus f of a. Okay. And now this is divided by mod of lambda and minus lambda times t of ej, right? Okay. What now?
So triangle inequality.
Okay, so how do you want to use triangle inequality?
Sir, there is a norm in the numerator, right?
Yeah, sorry. There is a norm in the numerator over here. Yeah, absolutely right. Yes. And in fact, without okay, all right. And this limit is equal to 0, right? So okay, so all right. So what is it that we want to
We can just distribute the denominator right inside the norm.
okay, let's distribute the denominator. But you see, if I want to distribute the denominator, then I have to.
And then continuity of norm. Take the limit inside.
Right. But how do I, okay,
Equal
all
to
right.
that partial derivative.
All right. So, okay. So because this is a real number, I can simply, so I don't want, so, okay. So because there was another suggestion, which is to use the triangle inequality, which means I would have to split the norm up there, correct? But remember, I'm taking a limit over here. So then it would have to be done carefully. But what you're saying is, let's just take the, because denominator is a scalar, right? So that scalar can simply be put inside the norm.
Yes.
Okay, so let's do that. So this is the same thing as f of a plus lambda ej minus f of a divided by norm of lambda minus lambda tej divided by norm of lambda. And this is equal to 0. Okay, so there is a slightly annoying matter here of the absolute value of lambda.
Sir, could we not remove it because the norm would take care of that anyways?
Exactly. So here is the thing. So I want to claim that, remember, because this limit is 0, right? Because this limit, or let's put it this way, because this entire, let's look at the previous step. Because this limit is 0, if I remove the absolute value around lambda, it wouldn't matter, right? Just think. Because this limit is 0, so let me just write this. Can replace this by or okay, maybe let me not do any shenanigans over here. Let me just say so. So let me just say, therefore, limit as lambda approaches 0 of f of a plus lambda ej minus f of a divided by lambda minus PEJ is equal to 0. Okay, so I did a couple of things over here. One is that if the norm, see, up until the first chain of equalities they were all equalities of real numbers. All right. But I'm saying if the norm of something approaches 0, then that vector itself must approach 0. Right. So I have removed the norm. Yes. And the second thing is that this absolute value, I can just remove it. Because if, for example, okay, let's if lambda is positive, then of course it doesn't matter. But if lambda is negative, then the first term acquires a negative sign if I remove that. But so does the second term, you see. And so the difference between the two terms becoming 0 just means that those two terms are equal. So what do I get? Limit as lambda approaches 0. Let's write it the other way around. We have answered our question. PEJ equal to limit as lambda approaches 0 of f of a plus lambda ej minus f of a divided by lambda. Okay, any questions so far?
Sir, could you repeat what happens in the case where lambda is negative? Like, why does it?
All right, so I did 2 steps. So I will just say, okay.
Hello, sir.
Yes.
So just instead of thinking about the positive and negative cases separately,
Okay.
we can just take that. Suppose I have simply lambda in one case and mod lambda in another case. Then as we have norm outside, anyway mod lambda comes out, right? So both of them are equal to the same thing.
I do not understand what you mean by that.
Sir, I mean, suppose we have 2 expressions. In the first expression, I have mod lambda in the denominator. And in the second expression, I have simply lambda in the denominator. And as I have norm outside, so both of them actually have mod lambda outside.
Now I understand what you're saying. Okay, so his point is that, okay, and maybe I should just do it this way. His point is that because I have this, in fact, I can maybe do this. Because I have this, I can simply remove the, so compare the expression, whatever is written over here with absolute value of lambda inside and just lambda inside, correct? So his point is the following, is that the equality is really true if I simply do the following. It's exactly the same. Because you see, if I pull the lambda outside, it being a scalar, it will come out as absolute value of lambda. Thanks. That's a simpler way of seeing it. Does that answer the question?
Yes, sir.
Yeah, okay. I mean, what I said earlier is also true, but it is more labored and unnatural. So what he said is absolutely true. So in other words, if I simply remove this limit over here, the equality is still true. There's no limit over there. All right, and then, but now look, what have I obtained over here, down here? So let's look over here. So I wanted to write down this matrix, the matrix of the linear operator T, which is the derivative linear operator at A. And I know that the columns of this matrix is just T applied to EJ. So T applied to EJ, I found a formula for this. But this should be a familiar formula. What is this?
Or the jth partial derivative of f. Right?
Right, but the jth partial derivative of f. Yeah, so remember that f itself is again, so letting f is equal to f1 up to fn, then this is really just equal to, let's just really write this down, limit as lambda approaches 0 of f1 of a plus lambda ej, f2 of a plus lambda ej, fn of a plus lambda ej. That's a vector, right? Minus f1 of a up to fn of a. All of that divided by lambda. And let me remove this thing from here. And but that's exactly equal to, so I can calculate this limit slot wise. We've seen that, right? Limits can be calculated slot wise. So the limit in the first slot is just going to be f1 of a plus lambda ej minus f1 of a divided by lambda. And that's precisely the partial derivative of f with respect to, that's what the partial derivative of, right? So this is okay, so just 1 second. So this is this is del f1 by del xj all the way up to del fn of del xj, of course evaluated at a. That is going to be the column vector. So the final answer is matrix of f prime of a, of course with respect to standard basis, is called the Jacobian matrix, and that is given as, so the first column, so notice this says clearly that it's the first column is all of that is the derivative with respect to the first variable. So this is going to be f1 x1 at a and so on. Okay, so f n with respect to xm at a.
Determinant of this has also geometrical properties, right?
Sorry, say that again, please.
Determinant of this matrix.
Right. So of course we have see, right now we're just sort of wetting our toes. We have lots of things to say about this. Yeah, so if we take the determinant of this matrix, since you mentioned it, let's just remember one thing for everybody to recall. The determinant of a matrix is a wonderful thing. It says many things about the matrix, but a particular fact about the determinant is very useful. Whether the determinant of a matrix is 0 or not tells you something about that matrix. But sorry, even before that, does the determinant make sense in general for a matrix like this?
No, from Rn to Rn.
So determinant makes sense only for square matrices. That is to say, when m and n are equal. And so the determinant of a matrix being 0 or non-zero tells you what fact about that matrix?
The singularity.
Yeah, what does that word mean? So what does that word mean?
Invertible.
So what is the statement?
So a determinant equal to 0 if and only if matrix is invertible or not invertible.
Okay, so let's say that carefully again. the determinant of a matrix is non-zero if and only if the function defined by that matrix, the linear map defined by matrix, is an invertible map. Okay, so this is going to be
So
a very
null space is zero, so derivative.
no. Let's not. Okay, there is no need to involve more and more words. Let's try to keep it as simple as possible. Okay, so the determinant being non-zero precisely captures whether the matrix is invertible or not. Okay, so when we come to the inverse function theorem, this is going to be a key criterion for us. But anyway, so we are still doing simple things. A basic property.
So, but the determinant is significant if and only if m and n are same, right?
Yes, exactly. So it applies only in that situation. Okay. Right now, it is not relevant for us. Basic fact: f prime A exists implies f is. Okay, sorry. So just 1 second before that. I should have stated this, so my bad. Let's go through this entire. Logic over here. So I am assuming that. So for this question, I am assuming that f prime of A exists, and that means that I started with this original limit being 0, and I deduced that. And I deduced that this final limit must exist, right? So I should really write this as a fact. So final answer. So we have proved. If f prime of A exists, then all partial derivatives f del fi by xj exist at x equal to A, and the matrix, and make up the matrix of okay. So we actually proved something over here, which is to say that if f prime of A exists, then all those partial derivatives have to exist. You notice the first limit existing made by force implied that this final limit had to exist. No, t ej is equal to that limit that had to exist, and its value is t of ej. And then this limit, by our earlier definitions, is precisely the bunch of partial derivatives, right? Of all the components of f with respect to xj. So this immediately brings a question. See, when we have proved that if the function is differentiable at a given point, then all the partial derivatives exist at that point. Immediate question. P implies Q. We always ask, does Q imply P? If all del fi by del xj exist at x equal to A, does it imply? Just a minute, just a minute, please. Does it imply that f is differentiable? And the answer to this question is no. This is quite a different thing from what happened in one variable, right? Because there is only one partial derivative. So these two are the same statements. So the point over here is that what can happen is that the derivative existing means that really the limit that we wrote over here, let's go back. This limit has to be 0, but the point is that there has to be a linear operator t such that that limit is 0. Okay. So what we are doing when we calculate the partial derivatives is that we are calculating, and let's not even take a function which is of which has many components. It's enough to consider the case where f is a function of many real variables, but it takes only one real value. See, if there is any difficulty, the difficulty will be seen even at this step, because after all, calculating the derivatives of a function that has many components, that simply means calculating derivative of each single component function. So this suggests that it is enough to just consider the case where there is a function f of many variables which produces a single real number. So what we are saying is that when we calculate partial derivatives, let's just say I have a function of just two variables, f of x and y. So when we calculate the partial derivatives of del f by del x and del f by del y at a certain point, what we are saying is that if I approach along two directions in these functions, in other words, this function is going to be some kind of topographical thing, some kind of mountain. The height, the mountains and valleys, and the height is the thing that gives the function. Calculating the partial derivative at a certain point along x or y axis simply means that you take this mountain and you slice it. When you slice this mountain, the profile that you get, that is going to be a function of a single variable, and you are going to calculate the derivative in the usual sense, right? So partial derivatives existing simply means that if I take two slices, a slice in one direction and a slice in a perpendicular direction, then both of those profiles have some derivative, they have a tangent line. So a priori, it seems quite a weaker thing than having a total derivative. So what could go wrong? Try to see if you can find an example. Okay. I'll maybe just get you started with this. To find nice examples of like this, there are many of them, but to find good examples, take some experience. So let me give you an example. Just take the function f of x equals x times y. All right. Now, do you think this is going to be a counter example to what we wanted? No, I mean, it's too nice a function. Okay. But see if you can do something with this function.
X by y.
You can try x, but what is the point? What is the point at which I am doing this? If I take x by y, then what is the point for which you are going to do this?
The partial derivative with respect to y might go to like infinite.
At which point? At which point?
At 0.
But at 0, 0, the function is not even defined.
Yes,
right? Here's another thing. You think of the square root of x function. Now the square root of x as a function of a real variable is problematic because it's defined only on positive side. So let us say I take the square root of absolute value of x. At the origin, do you have a tangent line? Okay, let's take another one because there is this square root which is positive, negative is obscuring the issue a little bit. Let's take the cube root of x. The graph of cube root of x at the origin, does it have a tangent line?
Yes.
Yes, it does. Does it have a derivative at the origin?
No.
No, because this tangent line is vertical, right? So there is something over there. So maybe you can see if you can combine these ideas for the, I asked you to consider the function xy. Anyway, so the answer is no. Answer But the answer is yes, under extra conditions. If all of your partial derivatives are there and if they are also nice,
If they're continuous.
then the answer is yes. And this is a fact that we will prove later on. So, okay, but first a basic fact. In analogy with one variable situation, which is if f prime of a exists, then f is continuous at a. So what does it mean to say f is continuous at a? What does it mean that f is continuous? So we have spent quite a bit of time discussing continuity, right? There are many different formulations. So we have inverse image of open set is open, etc. But now I have this in terms of f prime of a. So maybe I should do this in terms of limits, because I know some limit. So in terms of limits, what do I know about continuity? F is continuous at a precisely means that
Norm of f of a plus h minus f of a tends to 0 and h tends to 0.
Okay, so what you really want to say is that is limit as x approaches a. I mean, continuous functions. If x goes to a, then f of x goes to f of a, right? So let's do this in terms of h. So limit as h approaches 0 of f of a plus h is
F of a.
f of a, right? But this is really the same thing as saying limit as h approaches 0 of f of a plus h minus f of a is equal to 0. But that vector going to 0 is the same thing as its norm going to 0. Right? Etc. So this is a simple enough thing. So what do I do now? So proof. So this last fact is the one that we will prove. So I do the natural thing. So f of a plus h minus f of a. So let's call this t. So this is the thing that I have, right? This is the thing that goes to 0. Right, I mean, sorry, that divided by h.
Is that true that if all the partial derivatives exist, then it will be continuous?
Think about it. I am not so sure. From all directions.
I mean, from here on, if we take like h multiply denominator and numerator, then take the h inside, then the left limit will exist because the partial derivatives are defined and the h will go to 0. So the limit will also go to 0.
Okay, so why don't we do the following? Let us first, so his question is that can we weaken the hypothesis to saying that all the partial derivatives exist? Does that mean that the function f is continuous over there? Right? Why don't we first do this proof and then you can try to see if the proof can be weakened, right? Okay. So essentially what do we want to do? We want to bound this quantity and we want to show that it goes to 0. The point is that this quantity, so notice here, so this is what it is, no? That is what the given quantity is. So this quantity is what we have. I want to show that this goes to 0, but now I use triangle inequality. So this is less than or equal to f of, sorry. So we do this f of a plus h minus f of a minus th plus the norm of th. Okay. All right, so I want to show that this what I started out with goes to 0. So this is just equal. I mean, whatever is the inside quantity here, right? So it's enough to show that the right-hand side goes to 0 as h approaches 0. So what gives? So limit as, so let's look at this. The limit as h approaches 0 of f of a plus h, oops, minus f of a minus t of h. Can we show that this goes to 0?
Multiply a numerator and numerator by mod h.
Exactly.
This can be done also in that expression, right? In the very first expression. That also
Okay.
doesn't require the existence of the h.
But you see, okay. So, but okay, let's first finish this. Let's first finish this. So how does this help?
The left derivative. The left
So
limit
this
x.
one, right? So this one over here, you see, the point is that this first term does have a limit as h approaches 0. Or rather, sorry, the first, yeah. What am I saying? Yeah, what is the limit of the first term as h approaches 0?
Finite.
Well, it's actually,
Oh, okay. It's
Zero.
also 0.
it's 0, it's 0. So the whole thing is 0 times 0. So this is certainly 0. 0. The point though is that, see, I do need to have this division by h because that's the limit that I know to be 0. Right? Okay. And so what is the, so I'll just say 0 times 0, which is 0, if you wish. And what about the second term? What is the limit as h approaches 0 of th?
It's linear. So it's also 0.
Okay. So it's linear, so 0. Why the so?
I mean, t is linear. So as h goes to 0, the inside term will go to 0 and the norm will also go to 0. Linear maps are continuous.
Okay. So that is the point, right? So T is a linear map. And linear maps are continuous. This is one of the very basic things that we saw. So T is linear. Therefore, as h goes to 0, T of h goes to whatever h goes to. Sorry, that came out right. See, T is linear. So if x goes to a, then T of x will go to T of a. But here h is going to 0. So h is going to 0. So th will go to T of 0. T is a linear map. So equal to 0 because T is continuous, being linear. And so th goes to T of 0, which is 0 because T is linear. So done. All right. So regarding this other question that was asked, I will leave that for you now because I do want to get a little ahead, and we really should have done chain rule. So let's see how far we can get. Okay. So let's try the chain rule. So another basic fact is chain rule. So what is the statement of the chain rule? Chain rule means I need to have two maps, right? And I want to compose them. So let us say I have, and you see, I want to take the derivative of each one. That means the first map that I have, which is from U, and that is something in Rm. And then this map is in Rn. The target of that map will be Rn, but then I want to, I want to put together another map after that, right? And I want to take the derivative of that map at the, so this is A, and then there is this map F, which goes to map B in wherever. And then I want to take a map G from here to R, let's say K. The point is that this B should be in an open set, which is contained in the domain of the second function for me to apply my definition of the derivative, right? So I need to have as part of my hypothesis that F is a function which is, or rather this function G has as its domain an open neighborhood of the image of A. So V is sitting inside Rn. So is this okay? The first map is just from U to Rn, but the second map is from a neighborhood of the image of A to Rk. So that is what is given to me. So this is what is given, and so this is given. F is differentiable at A, G is differentiable at B, which is equal to F of A. Then what is the conclusion? Claim. First doing F and then doing G is differentiable at A, and what is its derivative? Exactly the same rule that we had earlier, but understood properly. So what is the rule?
The derivative of G valued at F of A times F dash of A.
Okay, what is the times here?
Matrix multiplication.
Yeah, so this is matrix multiplication. So could we have written this in the other order, F prime of A times G prime of F of A?
No.
No, because the matrix multiplication may not make sense, right? So this is matrix multiplication. So I will just write multiplication of or if I'm thinking of this as a linear operator, then it's the composition of those two linear operators, right? Okay, so let's start. Let's do the proof of this, and the proof is really not difficult, but we will need some ingredients along the way. So this is a new situation. Let's look at the old situation. What happened in the what happened in the single variable case? So recall one variable case. And what did we have? dz by dx equals dz by dy times dy by dx. What was the proof?
Last semester we proved it using the sequential criteria.
Okay, but I mean, let's just do this. Okay, so see, the point is what was involved over there. So this was limit as delta x approaches 0 of delta z by delta x, right? So what you wanted to do is so recall one variable case, and this is limit as delta x approaches 0 of delta z by delta y times delta y by delta x, correct? Of course, you have to ensure that delta y is not 0. And then we said that, well, product of limits is, limit of a product is product of limits, provided both of those exist. So you have to check that they both exist. And I'm home free, right? Except what do I have to justify over here?
Delta y equals to 0.
Right. So you see that second limit is perfectly good. It is the derivative of y. But the first limit is I'm calculating the derivative of, I want to say that it's the derivative of z as a function of y, but the limit is taken as delta x approaches 0. So you have to say make some noises as to why I can replace that by delta y. So why can I replace that by delta y?
Because y is continuous.
Y is a continuous function of x. That's a consequence of it being differentiable, right? So sorry, delta. Sorry, I'm just doing this heuristically because the point is that some analog of this will have to be used over there, right? So I keep making a mistake. So limit as as delta x approaches 0, delta y approaches 0. Okay. So I will just say heuristically. So let's put that on the side. So this is really just not part of the proof. So let's do some scene setting over here, right? Effectively, you see, I do have to do this kind of calculation. I have to take differences, right? So I have to take those error terms, the terms that go to 0. So what was the error term? So let's recall, let t is equal to f prime of a and s is equal to g prime of b. And remember, b was. So I was going to take limit as h approaches 0, etc., right? So let's take h and k small such that a plus h is in u and k small. I mean, the word small is really heuristic, but such that b plus k is in v. Okay, so what was it that we had? Remember, we had those error terms, what I call the remainder term at the top, right? R of h. So let's write down the remainder terms here. Remainder terms. So I had R, so let me call it here alpha. Okay, so sorry, 1 second. Alpha of h. What is that? F of a plus h minus f of a minus what? Come on.
T.
Minus t of h. And let us say beta of k is equal to g of b plus k minus g of b minus s of k. What do we know? Limit as h approaches 0 of alpha of h by h norms is equal to 0, as is the limit of k approaches 0 of beta of k divided by k. Oops, sorry. Okay, so this is sort of the scene setting. Just the nomenclature. What's the quantity that I should take? Any idea how to proceed? Okay, so we are running out of time. So let me just sort of say the punchline, which is that in order to do this, so we are going to have to do a similar kind of thing over here, right? Similar kind of, not exactly the same, but some bound, we will have to do some kind of bounding, some kind of estimations will have to be done. The point is that in estimating sizes of vectors, it will be very useful to have the notion of the size of a linear operator itself. So in order to do this effectively, it will be useful to have the notion of an operator norm. Okay. So far, we have not needed to define anything like this, but we will need to make this definition. So I think that we are out of time, so maybe I should just stop here. But okay, so just give me a minute. So what is it that I need to bound? Where should I even start? What should I start with? So which quantity should I consider? Look over here. In the one variable case, I needed to do delta z by delta x. What is the analog of that over here? So good to consider. I mean, I want to calculate the derivative of the function g composed with f, right? So how do I start? What do I do? This is the function whose derivative I want to calculate, g composed with f. So what do I do? How do I calculate the derivative of some function? I'm looking for a linear operator, right? So which linear operator and what property should it have? So really do think about this, because I want to write down this expression and then you can sort of try to take it forward from here. What expression do I need to consider?
So the like gf of a plus h minus gf of a.
Correct.
Minus st of
Right.
h.
So minus the linear operator that I think is going to be the derivative, right? See, I have the derivative is the unique linear operator that I put over there, which when evaluated at h and then I divide, etc., the limit turns out to be 0. Now I am claiming that the derivative is the composition of both of these. So I first have to do t and then I have to do s, and I have to evaluate both of these on what?
On h, sir.
On h. So I have to do this, and I need to show. So maybe I should start bounding this or something like that, right? And need to show that limit as h approaches 0 of gf a plus h minus gf of a minus st of h divided by h, of course norms everywhere, is equal to 0. Notice I only have h over here. I don't have any k anywhere. Do you think there should be a good k to consider? Again, look over here. When I wrote delta x, there was a corresponding delta y, right?
So the t of h, can you consider?
All right. Considering th is like saying f prime of a times h. Is that what I want k to be? See, k is the small difference that I want to take in the value of the middle variable. So what should I take k to be? So okay. So notice b, which is the value of f of a, which is changed. I want to change that by a small amount to something.
So maybe f of h.
Alpha h. That one.
But alpha h is really f of a plus h minus f of a minus t of h.
Yes, that is the k. I mean, norm of that is that also works as k.
Okay, think about it. Think about what should work. All right. So I think we should stop here. Of course, this is a standard proof, right? But do try to wrestle with it and see if you can do it yourself. Right. So let's stop for today.